Hey Calc students, this is Mr. Allen. Here's a quick video of my lesson on separation of variables. Today, Tuesday, we have our math league competition after school. Mr. Brewington's actually going to do that for me since I am not here. So our warm-up today, you may want to pause this. I'm going to just kind of go over things and try to keep the video as short as I can. So this was supposed to be, there's a little graphic here. It's actually SpongeBob and Sandy from the SpongeBob TV show, and it's supposed to be related to Valentine's Day. You can see there's kind of a heart thing there, but anyways, so here's our question, and it says a chemical reaction, etc. If there's 40 grams initially, then there's 20 or 35 grams after an hour. When will it be 75 gram? When will 75% of the compound be changed? So just to kind of jump to the conclusion again. So the solution is going to be the amount is equal to CE to the KT. K turns out to be the ln of 7 over 8 in this problem. C turns out to be 40. And then the final answer, again, you might want to pause this if you want to check. The amount of time it's going to take for 75% is 10 hours, 0.38178. So those are the kind of the answers. Again, you'd need to set that up, but I'm going to kind of keep things moving here. That was just a warm-up similar to what we've been doing. So today it's actually a little bit more of the same, except now we're kind of do a little bit more complicated separation of variable differential equations and solving them. So we've already done this, and we're just kind of stepping it up a notch. So again, you can see an example here. This is a differential equation that is not separated. You can see that there's x's and y's on both sides of the equation, but we can cross multiply, and now we have a rewritten differential equation where all the stuff in terms of y is on the left and all the stuff in terms of x is on the right. And then you can see some more examples of that below. The point being is you need to separate your variables before you do that integration step. You're not going to be able to integrate if a side has an x and a y in it. So let's look at our first example here. So we've got a differential equation. We can't just cross multiply here, so let me just show a little bit of the work. And again, I apologize, I'm doing this here from home. So let me get my red marker. So the first thing I'm going to do is just change that y prime to dy dx. And then the next thing I'm going to do is I'm going to move this x term over here. So we've got this. Now you can see that we've got y dy on the left, but there's that dx there in the denominator, so I can just multiply that to the other side. So these first couple of steps is just the separation of variable parts. So now I have my variables separated. So now I'm going to undo the differentiation through integration. So we're going to integrate. The antiderivative of y is y squared over 2. The antiderivative of x is x squared over 2. Don't forget your constant of integration. Now technically this is the solution, but I don't like it. I think it could be cleaned up. So what I'm going to do is I'm going to multiply both sides by 2. And that's going to make it a little bit better. So now you're going to get y squared equals x squared plus, and remember c times 2 is just c. And last but not least, I'm going to go ahead and rewrite this as x squared minus y squared equals c. And that's how I would write my final answer. No fractions, it's just a little bit cleaner. And so that's the general solution. If we want to check this answer, we know how to do that. We would just do the derivative of the answer I got, plug it back into the original equation, differential equation, and see if it works. And it does. Okay, the next one. Again, we've got a mix of x's and y's on both sides, so we're going to do what we can. So I usually like to get the y's to the left. So this y right here, to get it to the left, I'm going to have to divide it. So that's going to become 1 over y dy. and then I want to multiply that dx to get it on the other side, but then I have to divide the x squared plus 4 since it's a times. So, follow me here. You're going to be left with the x on the right-hand side on the top, and then the bottom, you're going to have that x squared plus 4, and then dx. So here in this very first, most important step, I have now separated all my variables. I've got y's on the left and x's on the right. So now we can integrate. We're going to integrate like this. And so we're going to get the natural log of the absolute value of y equals, we're going to have to do a little u sub here. So u is going to be x squared plus 4, and du would be 2x dx. Oops, let me get my picture out of the way there. But wait a minute, there's no 2 in the front there, so I'm going to make that 1/2 du equals x dx. And so now this is going to become 1/2 the integral of 1 over u du. So the left-hand side is still the natural log absolute value of y. The right-hand side is going to be 1/2 the natural log absolute value of u plus c. But remember, u is this, so we could rewrite this as the natural log of y equals, and now remember, this 1/2 is the same thing as doing the square root. We talked about this the other day in class, and then plus c. Again, this is a solution, and it's not bad, but I could e both sides. And so if I e both sides of this equation, what you're going to end up with is y equals c, and then the e and the natural log cancel out, and you end up with the square root of x squared plus 4. That's a pretty complicated one. Now I'll just tell you, on the AP exam, usually if you can get down to this step right here, you'll get most of the points. Usually the last point they want you to, they'll give you, they want you to get the solution in terms of just y by itself. All right, moving on. Okay, so this last problem, I'm going to let this sit here for a second, partly because I want you guys to be able to have a minute to look at it, but more importantly, I just realized I forgot my calculator in the other room, so I'm going to grab that. So I'll let you read that, and then we'll get started. So the main thing I'm wanting you to do is kind of ponder how to get question A there. Question A and question B. All right, so let's go ahead and see if we can attack this one. This is I created this problem, but I tried to use actual data to do it. It says solve the differential equation. So let's do that on this slide. I think I got two. Okay, I guess I only have one slide. So I'm going to go ahead and try to squeeze all this into this one. So right now the two variables are capital T and then lowercase t. I know that's a little weird, but the capital T here, that's the temperature. The little t is the time. So again, we need to separate the variables here. So this is going to be dt divided by t minus A. A is the ambient temperature, equals negative k dt. And so now we've got our variables separated, and now I can integrate. And when I integrate on the left-hand side, I'm going to get the natural log absolute value of t minus A equals negative k t plus a constant c. Now once again, what I want to do here is I'm going to e both sides, and so that's going to give me, well, the natural log and the e cancel, so you get t minus A equals, and then this is going to be c e to the negative k t. And so last but not least, we're going to get, I'm just going to add the ambient temperature over to the other side, so I'm going to get A plus CE to the negative KT. This is our general solution. That's a K. And again, the input variable here is this lowercase t, so maybe I'll put a little t in there. That's a t. So there's our solution, and that's our model. Well, not completely. Now we got to use the data to complete the model. So we know that the ambient temperature is 21. So that's going to go in here for A. So A is going to be 21. Maybe I'll do that in blue. We're going to figure out what C is next. So I'm going to put C here. Now we're going to do it initially. It comes out at 175 degrees. So that's going to mean that the rest of this is going to be e to the 0 because time is 0. And then that has to equal 175. And so we basically get C is equal to 175 minus 21. And just because Mr. Allen doesn't want to get this wrong, I'm going to make sure I use my, okay, so that's 154. So that's 154, that's C. Now we want to find K. So we got C, let's find K. Now we can use this other information, which is right here, that after 22 minutes it's 32 degrees. I'm going to move this up to here. So now I'm going to have 32 equals 21 plus C was 154 e to the, and then it's going to be 22 negative and then K. So remember there's that negative symbol up there, so I'm just plugging 22 in for the T, and I'm going to use my calculator to find this decimal. So I've got to do 32 minus 21, divide that by 154, do the natural log of that, and then divide by negative 22. And I get an answer here of K is equal to 0.1199571513. So there's my K. I'm going to store that as well. So I'm going to store that. I'm going to store that in A. And I know my C is 154. I'll write that down. And A is what, 21. So now we're going to jump to the next slide even though I'm running out of room. So for part B, the answer is the temperature at time t is equal to, move my face out of the way there, 21 plus 154, that was our C value, e to the negative 0.1199 t. I'm running out of room. So there's our solution for part B. And then you can see that I've already got that plugged in right here into Desmo. So here's what the graph of this is. We could graph this on our graphing calculators. And so let's go ahead and do that real quick. So I'm going to graph 21 plus 154 e to the negative point. Oh, actually I stored that in A, so I'll just type A, delete. So I'm going to do negative A x, and we're going to adjust our window appropriately here. So maybe I'll go out to 50 and up to, what, 450. I'm going to hit graph, and so my graph on my calculator is similar to the graph here. I'm going to double check that at time 22 we got 32 and it worked. And now to do the next part for C, we just want to do the value at 48. And so for part C, I'm just using my calculator, T of 48. I get 21.4827, and that would be minutes. Oops, I'm sorry. This is in degrees Celsius. Degrees Celsius. So that's the temperature in degrees Celsius. And last but not least, I threw a limit in here. What's the limit of the t function as t goes to infinity? Well, that's pretty simple actually. If the ambient temperature is 21, let's say it stays that way. Oops, that's supposed to be an infinity. Then the limit's going to be 21 degrees Celsius. I think that's it. Oh, I got one more initial problem. Darn, thought I was done. That's okay. We can do this real quick. All right, so dy, let's make sure we got that right because it says that the variable t, dt, is equal to negative ty. So we got to separate our variables. So it's going to be dy over y equals negative t dt. Now we can integrate. Again, we're going to get the natural log of y, and then negative t squared over 2 plus c. And that is actually a solution for this, but I'm going to go ahead and plug in our initial value now. So that's going to be the ln of y, which in this case y is 3. And then the rest of this is going to be negative something squared over 2 plus c, and that something here is 0. So it looks like c is going to be the natural log of 3. Okay, so let's rewrite this here. So we get the natural log of absolute value of y is equal to negative t squared over 2 plus the natural log of 3. And again, if I wanted to, I could both sides. And so we're going to get a final answer here of y equals, and then that's just going to be what? 3e to the negative 1/2 t squared. I think that's it. There's the graph. There's some of the graphs. Those are actually Gaussian curves. Anyways, thanks for your attention. Take care.